This is the last formal week of lectures for this course. I just wanted to go over the schedule and remind you that we have a midterm next week. So today I'm going to be covering, today and on Thursday, I'll be talking about topics which are not in the book. And these topics will also not be on the second midterm. They're more advanced topics, but I think in embedded systems you should be aware of these. So we talk about fault tolerance today. How do you build systems, and what are the issues related to having faults, not just in the design, but also in the other devices that make up your embedded system. And on Thursday, we'll talk about networking. Many of you already have used networking in your labs and projects, but we'll talk about some of the kinds of networks that are used in embedded systems, especially for real-time embedded systems. And then next Tuesday, we'll have a second midterm. Everything up until last week's lectures will be on the second midterm. And then on Thursday, we'll have many updates, and we'll finish up.
Is it material since the first midterm or?
No, it's since the first midterm, but not exactly, because there was I think one topic which we covered before the first midterm, which we didn't ask questions on the first midterm. So I think, actually going back, I think scheduling anomalies was not on the first midterm. Right? It was too close to the midterm. So so the last few topics in scheduling will be on the syllabus. And then everything since the first midterm, of course, will be on the syllabus. Yeah, I'll send out an email that talks about exactly what's the syllabus for the second midterm. Right? But very briefly, it's everything we've covered since the first midterm, which is since the 15th of March, plus I think the lecture on scheduling anomalies, but I have to check with Edward to make sure exactly what topics he covered that day. Okay? Okay, so are there any questions about the second midterm? Okay, so the other thing is we'll have many updates next Thursday, and those will be the same format as we had before, and we especially want to see what milestones you've been able to reach, and if you've had any problems, you should mention them, because this is the last checkpoint we have before your final presentations, which are scheduled for the 11th. Okay? All right, so before I get started with fault tolerance, I want to revisit this slide from last Thursday's lecture. So remember, we talked about timing anomalies, and there was a question about why there wasn't any prefetching here in this case. So I went back and tried to find documentation on this processor. And there's this particular scenario is not described completely in all detail, but from what I can make out, here's what happened. So the processor was a Motorola Coldfire 5307 processor. Okay. All you need to know about this is, for this anomaly, the structure of the pipeline is relevant. So if you remember what happened here, let me just quickly recap. You had some code executing on this pipeline, and so there's a sequential thread where block A of instructions is executed first, and then you have a conditional statement, and in the conditional you can either execute B or you execute this other branch, right? And what happened here was the case where the instructions in A hit in the cache, that led to a longer overall execution time than the case where the instructions in A missed in the cache. And this is rather counterintuitive, because you would expect that a cache miss is always the worst case, right? So what happened in the pipeline was that the pipeline is structured as follows. There's the top part, which is a fetch and decode stage. And this is where branch prediction happens. This is where instructions, the branch predictor decides whether it's going to speculate on a branch and how it will speculate. And then there's a buffer which holds instructions as they make their way out of the fetch decode pipeline. And then instructions at the head of the buffer will then go to an execute pipeline. Okay. So this is what happens in the processor. There's logically two parts to the pipeline, a fetch decode part and an execute part with a buffer in the middle. Okay. So what happened in the first case where you had a cache hit was roughly there was an instruction here which determined the branch target somewhere in the buffer. And now the instructions in A start getting fetched because you have a cache hit. They get fetched and they get decoded as well. But the instruction that's in the buffer is not yet executed. So the branch predictor kicks in, okay, because it doesn't know the branch target yet, and it speculates on what the value of the target that would be determined by this instruction is, and it starts fetching instructions from B. Okay? So what happens in the first case is A is sitting here in the fetch decode stage. The instruction which determines the branch is ahead of A, but it's in the buffer. It hasn't executed yet. The branch predictor therefore speculates and starts fetching stuff from B. Okay? So that's the first scenario. Now in the second case, you have the same setup where the instruction that determines the branch target is sitting in the buffer, waiting to be executed. But now what happens is you hit, instead of a hit in the cache, you get a miss in the cache for A. So the fetch pipeline is basically stalled, waiting for instructions from A. Okay? So there's nothing here. Therefore, there's no branch to speculate on. The instruction that determines the branch target goes ahead and executes, right? And by the time you start fetching and filling the fetch pipeline with instructions of A, this has already executed. The branch target is known, and therefore, this starts after A. It starts fetching the instructions from B. Okay, so that's what happened here. In the case of the instruction cache miss, the fetch pipeline was basically idle. Nothing was happening there, which turned out to be a good case because the instruction that was in the buffer got executed, and then that decided the branch target. Okay? So, any further questions on this slide? I think, Nima, you were the one who raised this. So you're satisfied? Okay. All right, so now let me go to the new topic for today, which is fault tolerance. And I'm going to base this lecture on a guest lecture that was given by John Rushby, who is a researcher at SRI, which is a research lab near Stanford in Menlo Park. So John gave this lecture in 149 2 years ago, and he covered a lot of great topics. I don't think we have time to cover the entire breadth of the topics he talked about today. So I'm going to focus on certain selected topics, but I'll post the entire slide set on the website, so you can go through it at leisure later. Okay, so this lecture is about tolerating faults that arise in various components of your embedded system, like mechanical defects in sensors or actuators, electrical defects, bugs in the code, everything. Okay, so we've all talked about the various situations where bugs led to failures, and there's other situations where there were faults in devices that led to failures. So what we're going to do is talk about what are some scenarios, real cases of faults appearing in the field, with a focus on the avionics domain. So we'll talk about various situations in aircraft where there were dangerous situations, and we'll talk about how they arose from faults and how those problems can be mitigated. Okay, so we'll start talking about faults and sensors first. Okay. So let me start with an example. A couple of years ago, there was an incident on a flight from Singapore to Perth, Australia. So this is the code of the plane which was involved in the incident. So if you actually Google this, you probably will find more information about what happened. Basically, suddenly the plane started pitching violently, and some of the passengers weren't wearing seat belts, so they got thrown around the cabin, and there were several serious injuries. It turned out once they looked at the black box recorder and tried to figure out exactly what went wrong, it was a problem in how faulty sensor data were being handled. So in this case, it was a problem involving the so-called angle of attack sensors. So for those of you who don't know this term, so the angle of attack, if this is the wing of the plane, and you draw a chord through that wing, okay, so the angle of attack is going to be, suppose the plane is flying that way, the angle of attack will be the angle between the direction in which the plane is trying to fly and the direction in which it's meeting wind resistance, right? So that's the way that the air is flowing, and so this angle alpha is going to be the angle of attack, right? It doesn't have to be, this doesn't have to be level with the ground, right? So in fact, this line could be horizontal to the ground, and this could be tilted that way, right? But the basic idea is it's the angle between the direction in which the wing is moving and the direction in which it's meeting air resistance. So now there were these sensors that were used to compute the angle of attack on the front of the plane, one on the left and two on the right. Okay, so let's call this sensor number 1 on the left and sensor 2 and 3 on the right. And always in embedded systems, especially in safety-critical embedded systems, they use redundancies in order to deal with faults. So you don't have just one angle of attack sensor, but you have multiple sensors, so that if one of them fails, then you can use the others, readings from the others, to get a reliable reading. Okay, so what you really want to do is you want to get a consensus on what is the right value for the angle of attack. Okay, and it has to deal with a whole bunch of errors and noise situations. So, so the question is, in this case, what really happened was, so the question is, how do you actually do this? So in this situation, what happened was these sensors were being sampled at 20 hertz. And so you would get so 20 hertz is what, 50 milliseconds, something like that. So, so every 50 milliseconds, you would get 3 readings from the 3 sensors, and you compute the median of those 3 readings, and you compare each sensor to the median value, and compute the difference. Right? And if the difference was larger than a certain threshold, and that difference persisted for a duration of 1 second, so you took many readings over a single second at 20 millisecond intervals, and if you found that there was this discrepancy with this one sensor from the median that existed over the entire period of 1 second, then chances are that that sensor is faulty because it's consistently giving you a reading which is off from the others. And so in that case, the protocol they were following is they would flag that sensor as faulty and then ignore it for the rest of the flight. Okay, so effectively then they would be flying with 2 sensors. Now, assuming that you never had this situation, all 3 are okay. The way the control software worked is it used the mean of sensors 1 and 2. So if you remember, sensor 1 is on the left and sensor 2 is on the right. So they're trying to get readings from 2 different parts of the plane. And then they compute the mean of that, and then the mean becomes the angle of attack. Okay? And then they have other things. Suppose the difference was a little larger, then we use the previous average value for some time, and so forth. All right, so what happened in the failure? There were 2 spikes in the readings. The first spike was shorter than 1 second. So the thing is that this part didn't kick in because the difference has to be larger than 1 second. Okay, and the second spike in reading, so a sudden increase in the angle of attack, was still present a little while after the first. Okay. So what happened was there were faulty sensor readings that indicated that the angle of attack suddenly jumped, right, which could indicate that the plane is suddenly veering off course or something like that. So what happened was that there was some protection system which then got activated, and it suddenly caused the plane to, I think, drop in altitude a little bit. Okay, so this was basically it was there was faults in sensors that were then inappropriately handled, and that was the problem. So this is actually dealing with faulty sensor data is a tricky situation, because right now, all of the systems that are out there, there is no one solution. There's not a solved problem. So everyone has customized problems to whatever system they're building, and there's a lot of work out there, but it's still I don't think there's any definitive solution to dealing with data from multiple sensors. So I'll let you read the second example later. But basically, one way of dealing with a faulty sensor or sensors which have noise is to think of their value not as point values, but as intervals of values, right? So just imagine if you had a sensor that reported that its value is in some interval, 0.5, 1.0, and the value could be anywhere in the interval, but at least the sensor tells you that that this is the confidence that it has in its value, right? So if a sensor reports a value with a large interval, then chances are that the value is very noisy, right? And if it just reports a value in a small interval, then the value is likely to be accurate. Okay, so let's go with this and just see how one possible fault-tolerant solution can work if you assume that your sensors give you not point values, but interval values. Okay? So, so there's an algorithm that was proposed by Keith Marzullo back about, I think, 20 years ago, around 1990. The idea is you have n sensors that provide you each with an interval that they think the value of the parameter that is being sensed lies in that interval. So you have n intervals coming in, and some of those sensors can be faulty, right? And so he came up with a protocol in order to tolerate a certain number of faults in n sensors. So let's say you have at most f faults, and the probability of having more than f faults is really small, so you ignore that. Okay, so the basic axiom is that if a sensor is not faulty, then the interval it provides will contain the true value. Okay, therefore, if I have a bunch of intervals coming in, and let's say I have 10 sensors, and at most 2 of them can be faulty, then if I take the remaining 8 non-faulty sensors, if somehow magically I knew what they were, and each of them provides me an interval, I can simply intersect the intervals and get a tighter interval which is guaranteed to have the correct value, right? Because every non-faulty sensor contains the true value in its interval. Okay, so the basic idea is to tolerate if you have n sensors and you want to tolerate f faults, then you choose an interval that contains all overlaps of n minus f. Okay, this is being a little bit, so since you don't know exactly which are the n minus f non-faulty sensors, you basically consider all possible n minus f sets of sensors and look at their overlap, and then you compute an interval that contains all overlaps. So let's look at an example here. So let's say you have 4 sensors, S1, S2, S3, and S4. Okay, and each of these line segments, the black line segments, represents an interval. Okay, so for sensor 1, this is the interval that it reports. For sensor 2, this is the interval it reports. For sensor 3, it's this large interval, and for S4, it's this small interval. Okay, so now suppose I assume that at most one of these sensors is faulty. Okay, so I know that at least 3 of the sensors are non-faulty, right? So I can look at all sets of 3 sensors and take their intersections and see what I get. So here I can take S1, S2, and S3, And if I intersect these intervals, so the interval for S1, the interval for S2, and the interval for S3, I get what's inside in between the blue dotted lines, right? So this width, this is the interval which S1, S2, S3 all agree on. Okay. The only other set of 3, so what you can do now is compute all subsets of size 3, and assuming there's at most one fault, you have to have, for any valid subset of 3 that corresponds to non-faulty sensors, they have to overlap, right? All three of them have to overlap, like this. So if I, for example, if I took S1, S2, and S4, then the intersection of S1, S2, and S4 is empty, right? And so it can't be that S1, S2, S4 are all non-faulty under the assumption that there's exactly one fault. Okay? So the two possibilities are either S1, S2, and S3 are not faulty, or S4, S3, and S2 are not faulty. Okay, those are the possibilities. So either the value lies in between the blue lines or it lies in between the red lines. Okay? So, so now what Marzullo's algorithm would do is it would say, okay, what I know is the value is either here or it's here. So I'm going to be conservative, and I will take the convex hull that contains both of these intervals, the convex hull of both of these intervals. So this is 1D convex hull, right? So you're just going to take the large interval that starts here at the left end of the blue interval and ends at the right end of the red interval. Okay? So that's going to be the entire range of values. And so Marzullo's algorithm would say, okay, to tolerate F faults, I'm going to choose the interval that contains all possible overlaps of the n minus F hypothesized non-faulty sensor sets. Okay? So everybody clear on this? This is his scheme. What's good about this scheme and what's bad about this scheme? Karthik? You need to know how many are faulty. Yeah, so you have to have a good estimate of the maximum number of faults that can show up in your system, right? Typically, the way people try to do that is they assume independence of faults. So they assume that the sensors will fail independently. It's not always a valid assumption. And then they try to engineer the sensors so that the faults happen rarely. So they try to estimate in testing. They say, okay, I tested the sensor 1,000,000 times and it failed once. Okay, so I have a 10 raised to minus 6 probability of the sensor failing. And then if I have 2 sensors and they fail independently, then it's 10 raised to minus 12 is the probability of failure. Okay. Now, agencies which certify these kinds of safety critical embedded systems, like the FAA in this case, they'll specify certain reliability requirement, right? So you might have heard things like, I want 6 nines reliability, right? And what that means is that really I want the system to work with probability that, right? 0.999999, which is a probability of error should be 10 raised to minus 6. Okay, so typically you try to engineer the system to meet the requirement, right? And so the companies that build these systems would say, okay, I make an independence assumption, and then the probability that 2 sensors fail is 10 raised to minus 12. Okay, that's a really small probability. I'll assume it will never happen. So I'll design my system to tolerate 1 sensor failure. Okay, so that's how they do that. It's not, so again, as you pointed out, it's not a foolproof assumption, but let's go with that. Let's assume that that's okay. So you have default model of 1 sensor failing at most is okay. 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 So good point. So if you have n sensors, n is large, you basically have to look at n choose f possibilities. So consider all subsets of the n sensors, and that can grow combinatorially if, especially for large n and somewhat large f, right? But if f is 1, then it's not too much. Okay, but that's also a problem. Yeah. What else? You may not be able to shrink the interval that much. Yeah, exactly. So what's happening here is you're actually growing the interval, right? So each time you do this, each time you have a fault or there's some noise, the interval that you compute will then be, if you do take this union, it's large. And now you have even less confidence in the result, right? So suppose your algorithm requires the sensor reading to be somewhere in the blue range, and you have a test on that value, right? So let's say this end, the left blue end is 1 and the right blue end is 2. And you have a condition in your code which says if the sensor value is between 1 and 2, do this. Otherwise, do something else. Right? If you have this big interval, you can't tell whether the sensor value is between 1 and 2 or it's outside the interval. Right? And so, so making decisions on sensor values becomes much harder. Okay. Anything else? Okay, so those are all problems. I guess the good thing about this scheme is that the interval certainly contains that point, right? The true value. So that's the interval that they would compute with Marzullo's technique. Now, there's one more problem with Marzullo's algorithm which didn't come up, which is that it's not very robust to slight perturbations in sensor values. So suppose for example, the sensor 4, its reading is slightly off. So let's say at one time instant, this is the interval sensor 4 reports. And so Marzullo's algorithm would compute this entire interval. At the very next time instant, let's assume that the interval is slightly to the right. Okay, so it's basically the interval falls to the right hand of this dashed line. So the interval falls somewhere there. Okay. So now the problem is that S4 no longer intersects with S3. The interval for S4 in the previous case overlapped with the interval for S3, but in this case there's no overlap. So if you apply Marzullo's algorithm here, you're going to end up with this interval. Okay. Now there's nothing wrong with this because in fact this actually will contain the true value, right? So the only set of 3 non-faulty sensors that overlap are these 3. So you know this interval will contain the true value. So the problem is not with the accuracy. The problem is that suppose at time instant, let's say at time 1, this was the interval I had, and at time 1.05, 50 milliseconds later, this is the interval I have. There's a sudden jump in the value, right? So you have the same sensor reading, but then you have a sudden spike in the sensor reading, okay? This is not a very nice property from the control point of view. So typically in control, there is this condition which makes various things in control easier. Okay, and so it's called the Lipschitz condition. Does anyone know what this is? Yeah?
That's actually like a small change in your...
Okay, exactly. A small change in input results only in a bounded change in output. So more precisely, if you have a function f, and this is your output function, then if your input changes from x to y, okay, then your output will go from f of x to f of y. And what we want is this change in the output should be bounded by the change in the input. So the absolute value of f of x minus f of y should be less than or equal to some bound b, some value b, times the difference between x and y. Okay? And typically you want b to be small, so that you have, if x minus y is small, then f of x minus f of y will also be small. Now here what's happening is the change in input is the change in the value of S4, right? So here there was a small change in the value of the sensor, of the fourth sensor. So the interval changed just slightly from the one on the previous slide to this new interval. So there was a small change in x and y, going from x to y. But if you look at f, if f is the output of Marzullo's algorithm, there's a big change in the value of fx to fy, right? From a large interval, it suddenly jumps to a really small interval. Okay, so Marzullo's technique, although it's conservative, it has it guarantees that you'll have the correct value here in this interval. It fails this Lipschitz condition, and so it was a good first step, but it's not the final answer in dealing with faulty sensors. And there's been a number of people who've come after that and proposed various refinements of the scheme. Okay, but the basic idea of having sensors return intervals of values rather than point values, that's a useful idea in dealing with noisy or faulty sensors. Okay, so that's the first story. Okay, the second one we'll talk about is to do with computation. So we talked about faults in sensors. Now let's look at a case where there was a fault in the compute part of your embedded system. Okay, so here's another case, another plane that was in this case going from Hong Kong to London, and so what happened was towards the end of the flight, this is a long haul flight, right? Towards the end of the flight, as it was getting close to London, two of the engines flamed out, right? And then the crew saw that they were low on fuel, and two of the engines are gone, so they declared an emergency, and they found the closest airport, which was Amsterdam. Okay, so they landed in Amsterdam, and then when they did the post-mortem, they found that it was a problem with computers on the system. So there are these computers called fuel control monitoring computers, FCMCs. Okay, and again, for a safety critical embedded system, you have redundant computation. So you try to budget for the case where one computer fails, and then you have a backup computer that can take over, right? And so in this case, there were two FCMCs, and they always cross-compare their results. And they have some scheme of determining who is correct. So the healthy computer. The healthy computer is the one which actually writes to the data bus. Okay, so writes the control outputs to the data bus. Okay. Now in this case, what happened was both have them had fault. Had some. They were somewhat faulty. They had fault indications, and one of those two was unable to drive the data bus. So the fault was actually it was not able to put values on the data bus. But in the protocol between these two computers, this faulty computer was the one that was judged to be the healthy computer, right? So there was computer number one that could actually drive the data bus and could write the values. And it was deferring to the other computer and saying, "Okay, you write values on the data bus, right?" And that was really what the problem was. Okay. Now then you might think, okay, well, do they have some other backup for this? And in fact, they did have another backup, even to the FCMC computers. But the backup systems were not invoked because there was a bit somewhere that was set saying at least one of the FCMCs is active, it is not faulty. So there's no need to activate the backup, right? And so this is really a problem with the system that was being used to deal with faults in this case. Right? Okay, so now how do people actually deal with faults in practice? There's two common approaches. The first approach is what we saw earlier, which is self-checking pairs. So you instead of having one computer do the task, you have two of them, and they generate output at periodic intervals, and they compare their outputs. And each time they disagree, there is some some protocol that's followed. So one possibility is that whenever they disagree, they shut down and they defer to some other backup system. Okay. Another approach to take is called n-modular redundancy. This is a very popular, very classic approach. So here you have n computers, and so maybe n is equal to 3, and each one of them is doing the same thing. So it's working on the same sensor data and producing the same actuated outputs. And at every cycle, basically, all computers will compare their results, and the majority wins. So if you have 3 computers and 2 agree on one value and there's one outlier, then the outlier value is ignored, and the common value is the one that's written on the bus, right? So that's one approach. This is called exact match voting. Another approach is so exact match voting works for discrete outputs, right? But for outputs that are numerical values, it's possible just because numerical computation is imprecise, and if all the computers get slightly different data values, if you don't make sure that they all get the exact same sensor inputs, the outputs could be slightly off, and so in that case, you could use a different scheme like averaging the outputs. Okay, so that's one issue. You have to figure out whether you're going to go with exact match voting or you'll average the outputs. Another thing to think about is, are these computers synchronized or asynchronized? So if the computers are synchronized, then what it means is that they're synchronized in time. So they will read the exact same sensor inputs, and they'll run the same code on those inputs, and therefore they expect to generate the same output. The only reason they won't generate the same output is if there's some fault in the hardware or something like that. Unsynchronized means you don't force the computers to read exactly the same sensor input. So they could get sensor inputs from slightly differing time instance, and so the outputs are expected to be slightly different, and in that case, you have to deal with it. Okay, so there's 2 questions here. When we do something like n-modular redundancy, you have to figure out whether you want to do something like voting or averaging, and the other choice is whether the system should be synchronized or unsynchronized. Okay, so in the avionics domain, these computers are typically called channels, and again, the axiom people use in designing these systems is that failures are independent, and they try to make sure as much as possible that the independence assumption can be trusted. So they separate these computers physically. They provide different power sources, different cooling systems, whatever, right? So they try to make them as independent as possible and reduce any subsystems that both will depend on. Okay, so let's go with that axiom for now. So let's consider one example. So the F-16 aircraft followed this model of having unsynchronized designs. So in this case, you had these channels, computers that sampled sensors independently, and then they would go off and compute and then compare their outputs. Okay, so as we discussed earlier, if you have unsynchronized systems, you can't really expect the outputs to be perfectly matched all the time, right? And so there's lots of problems that can arise here. So first of all, you can, over time, if the systems are not synchronized, if they are, so if you have, let's say you have 2 systems, and each of them is getting values from the same sensor, but they're sampling it at different times, right? So there's some variation in the sensor value, but computer 1 reads it over here, and computer 2 samples it maybe a little later, right? And let's say this is, let's say it's velocity. Okay, and internally, let's say these computers are integrating that value, so they're computing position. From this velocity reading. Now, of course, what can happen is if these are sampling slightly different values. And if it just happens over a short period of time, then, and these values are not too different, then if these time instants are close enough, then you would expect that even though you're integrating over these values, if you're doing it for a small time interval, then the drift is bounded, right? But if you do it for a large time interval, then the drift can get quite significant. And in that case, these two computers would disagree significantly on the position of the plane, right? So you can have, if outputs depend on values that are time integrated, then if you have unsynchronized designs, there can be a large drift in the outputs over a significant period of time, okay? And there's lots of other problems that can arise. There's clock drift. So if you have two different clocks that are operating these two computers, and you don't have a precise time synchronization between those two clocks, they can drift over time, and that can affect when the computers may think they're sampling at the same time instant, but they're actually not sampling at the same time instant. Okay, so you often have to, in this case, you know that these things will get out of sync, so periodically they have to synchronize their clocks and check the values that they're reading, that they're close enough. Okay, so the point is, if you have unsynchronized systems, you need a lot of other stuff to make sure that the reason for the outputs disagreeing is really that there's a fault, and it's not because of some coding problem, just not because of the way you design the system. Okay, so the strange thing is sometimes you start with an application and then you keep writing all this code to deal with drift in sensors and redundancy and things like that, and it's been found that in some cases 2/3 of the code, 70% of the code, is not actually doing the task, right? It's just dealing with all the redundancy and reliability stuff. Okay, so that's what an unsynchronized design looks like. In this case, you have 3 computers, and each one is computing on an independently sampled value from the same sensor, but independently sampled. Okay, and then they all try to control a single actuator. Okay, so here's one problem that happened with an unsynchronized system. So you had multiple computers. This was a test flight of the F-16. You have multiple computers, and they're all sampling the sensor at different times. And there was some skew in the samples, because of the lack of synchrony. And what happened was every computer declared that the other ones failed, right? Because there's not going to be any agreement. Okay, so then finally, I think there was a manual intervention. Actually, there's something else. So in this particular setting, there were a bunch of digital control computers, and those are the ones that were not synchronized. And then there was an analog backup. So what had happened here was each of the digital computers declared the other ones failed. And then the system should have been designed to go back to the analog backup. But in their recovery system design, they hadn't anticipated that two of the channels would fail simultaneously. So they just hadn't thought about that. And so even though there was an analog backup, that wasn't selected. And so ultimately, I think the pilot had to take control and fly the plane home with just a single computer. And so the point here is that there really wasn't a fault in the system at all, right? The problem was just in the way they designed their fault tolerance solution, okay, which was using unsynchronized systems. So, this is another a slightly different problem, but it's worth going through this example also. So in this case, what happened? There was again a repeated indicator during flight of a channel failure, so the computer failure, and that was designed to a particular software, a piece of software. Okay, and so when they looked through it, they saw one of the channels was taking a completely different path. So the trajectory it was computing for the plane was completely off from the other two. And so there was actually voting. Okay, so it was something like this where you had multiple computers and you were doing voting at the output. Okay, so one computer was completely off and the other two was in sync. Okay, so you would expect that at the software switch it would take the majority vote, right, and go with that. And this is actually a system in which they had done extensive simulation and testing. But they found that this problem still persisted, and it turned out that the problem was in the recovery code, right? So they had made a mistake in the majority voting code. Even though they compute the majority vote at the switch, the value that was being used was the one that was the unvoted value, right? So not the majority value. So so I think one of the things that you see here is that first of all, you have to have some fault tolerance system to deal with faults in the field. That's a given. But all of these instances are cases where they actually had a fault tolerance subsystem, right? They had some software dealing with faults, and that software had a bug in it, or that software was not correctly designed, right? So you have to be really careful about designing the right fault tolerance solution. When you if you have a checker in your system, you have to check the checker, right, and make sure that's correct. You can't just assume that's going to be okay. Okay, so this is the bottom line. So nearly all failure indications in the flight tests of the F-16 were not really due to actual hardware failures, but they were due to design oversights. Okay, especially concerning this particular unsynchronized fault system. Okay, so what's the alternative? So the alternative is to have a synchronized design. So a synchronized design would mean you do have multiple computers, and they sample the same sensors, but they sample the same sensors at the same time instance, right? And then you duplicate the voting as well, and make sure that so in this case you would expect the values, output values, to match more often than they did in the previous case, because you're sampling the same sensor values at the same time instance. Okay, so so there are systems that use synchronized fault tolerance systems, like in the 777, and so it's definitely better. It's a more predictable way of doing fault tolerance, right, to use synchronized systems, but you need a whole bunch of things to make sure that synchronized fault tolerance works. Okay, so the first thing you need is clock synchronization. And so you have these multiple computers on board. Sometimes these computers are physically distributed so as to make them independent, right? So remember, for independence, you try to make sure that a computer has its own power supply, its own cooling system, whatever, right? So you have all these physical constraints that will dictate that the computers have to be physically separated. So you often have a network connecting the computers, and you have to make sure that they're time synchronized over that network. And you have to, we have protocols like NTP today, which synchronize computers on the internet, but the granularity of synchronization is not that high, right? So if you need nanosecond scale synchronization, then you need protocols, time synchronization protocols that are even more higher fidelity. So we'll see some of that on Thursday when we talk about networking. But in order to have this work, you need clock synchronization. You also need to distribute sensor values. You need to make sure that each of these sensor values is the same. So if you have the computers all together and you're connecting a single wire to each computer, and the wires are short enough, there's no network in the middle, you can say, okay, well, it's quite likely that the values they get are the same if they sample them at the same time instant and the clocks are synchronized. But suppose the sensor is off at the tip of the wing of the plane, right? And so to bring it, you probably have to run a wire. Maybe you're running actually a bus where you have multiple sensor values being put. There is some latency to get from a sensor to the computer. And so what you need to make sure is not only the computers sample the sensor value at exactly the same time instant, but the time it takes from the sensor to transmit that value to the interfaces, the network interface of each of these computers, even that time should be the same for all three, right? Because only then will you be absolutely sure that they're reading the exact same sensor values. Okay? So you need to be able to do that. You need to do distribution of sensor values. And you need to be able to deal with all kinds of faults. Okay? So Byzantine faults are those where the faulty behavior is a little adversarial, right? You can't make these nice assumptions that it's all of these faults will happen independently with the same probability and all that. Okay, so there's a very well developed theory of distributed systems that deals with these issues, and we'll touch upon some of that on Thursday. Okay, so let me talk about one more issue, which is, it's not exactly a fault tolerance issue, but it's more of just a reliability and safety problem, but it's extremely important for embedded systems, which is dealing with faults that arise due to interactions with human operators. Okay, so oftentimes when we design an embedded system, these systems are designed to be interactive, right? There is a human in the loop. So avionics is a great example. You have a pilot, and the pilot actually is making the system go into different modes by setting switches. Right? The pilot can take control at some time and fly the plane for a while. So the pilot can actually determine the parameters like the airspeed and so forth. Okay, so that's one place where the pilot is in the loop of your system. Cars are another example, right? So the driver is in the loop. Medical devices, you have doctors who are setting various parameters on surgical apparatus, or on setting parameters in a defibrillator or a pacemaker. So what you need to make sure is that each of these human operators have an accurate picture of what's happening inside the computer, right? Because any action they take can change the state of the computer, and if they don't have a good picture of what's going on inside, then bad things can happen. So we're going to look at some examples of problems that arose in an avionics context. Okay. So there's been well documented situations where in aircraft incidents and accidents, people ultimately said, the real cause of this was human error. Okay, in fact, it turns out that the human error is the dominant cause of accidents or near misses. Okay, so you can actually, if you, for example, you can go and Google F-22 crash, and you'll find this short 2-minute clip of an F-22 that's flying, and then at some point its tail starts just violently shaking up and down. Let me try to find it right now, because it's instructive. The plane is approaching, and now you'll see that the back of the plane starts really shaking. It wasn't that, I think the video was not that high quality, but you can see that the tail portion of the plane was just flapping, and then you can see that it's on fire. The video is not great, but that happened, and that happened because of a human-computer interaction issue. Okay. So now the problem typically is that it often turns out to be a UI problem, that the user interface is such that the pilot doesn't actually know what the state of the plane is, right? What mode it is in. Typically you have state machines, right? And you need to know that the state or the mode that the system is in is what the pilot thinks it is in. Okay. And so this situation where the pilot thinks the plane or the the control system is in one state, whereas the system is actually in a different state. So there's a mismatch between what the pilot thinks and what the system is actually doing. This is known as a mode confusion. Okay? It goes under these two names, automation surprise or mode confusion. Okay, so we'll look at a particular instance of a mode confusion problem. So this actually happened in a commercial flight. This was a McDonnell Douglas 88 plane, and the problem is referred to as an altitude bust. Okay, so this is an avionics term. So what this effectively refers to is a plane that is not flying at the altitude it's supposed to, right? So as many of you would know, the way in which multiple aircraft share the same airspace is that you have the airspace divided up into levels, right? So air traffic control tells a particular plane, okay, you're clear to fly at 32,000 feet, right? And maintain this altitude. And that's to make sure that some other plane could use the airspace above and below, right? So a bust is a situation that happens when a plane does not stick to that. It attempts to go up or down into some other plane's airspace. Okay, so this is what happened in this situation. So we'll go through some terminology, and then I'll describe exactly what happened, and then we'll analyze why it happened, and we'll see how the topics we studied earlier, like model checking, can be useful in preventing these problems. So in the control system of this plane, I think they're redoing the 4th floor of Corey, so it's going to be a little noisy. Okay, so the control system has various modes. So there are modes that relate to different functions. Okay, so there's a bunch of modes that are called pitch modes. Okay, the function of this is to determine how the plane climbs. Okay, so one possible value of the pitch mode is v speed, vertical speed, which basically the pilot specifies the plane must climb at this vertical speed, which is typically given in feet per minute. So the pilot says set a vertical speed of 1,000 feet per minute, right? And so the pitch mode becomes the plane is climbing and the vertical speed is 1,000 feet per minute. Or the pitch mode could be something like this. I don't know what I is, but this basically maintains a certain airspeed. So it's moving forward with a certain fixed speed. And it's climbing while doing that. And then you have altitude hold, which is you've reached a certain level, just hold that altitude. Okay, don't climb. So the pitch modes can be in those three values, and I think there's a couple of other values that they can have. Then there's a different mode. So the way to think about this is you have you can think of this as a state chart, if you will, where you have two processes, one of which is the pitch mode and one is this other thing called altitude capture mode. Now the altitude capture mode has a different function. It's determining whether there's a limit to how much the plane climbs. So there are two possible values for this. It can either be armed or disarmed. So when the altitude capture is armed, the plane will climb to a certain altitude that's set, and then it'll just stay at that altitude. And so basically, if I say, for example, the altitude capture should be armed to an altitude of 20,000 feet, then the plane may be at 10,000, so it climbs to 20,000, and then it must just stick there. So it should automatically just stay there. Right? The pilot shouldn't have to change the mode. Okay, that's the meaning of altitude capture. Then what's confusing with this particular system was that there were two modes that were called altitude capture, effectively. So one was this mode we just talked about, but there's also a value for the pitch mode, which is called alt cap, and the function of that is to end a climb. Okay, so as you will see, the confusion arose because of some interaction between these two. Okay, but the point is, if the altitude capture mode is not armed, then the plane will keep climbing. Okay, so here's what happened. So the plane was supposed to land. So the crew had tried to land and they had missed. and then it went back up. So it climbed again and then leveled at about 2,000 feet. And now I'm going to describe the incident. And the way we'll go through this is the incident involves two entities, effectively. One is the pilot. So everything the pilot did is in blue. And everything in red is an action taken by either air traffic control, so some other human controller, or by the automatic system. Okay, so what happened first? Air traffic control, after the missed approach, said, okay, now you climb and maintain 5,000 feet. Okay, so the captain of the plane is trying to do this. So he sets the altitude to 5,000 feet, target altitude, and then this internally, so he makes a setting internally that causes altitude capture to arm. So this happens. Okay, so effectively now the plane is configured to go to 5,000 feet and stay there. Okay, this is the desired behavior. This is what we want the system to do. Okay, then what the pilot does is the pilot is now setting the speed of the climb. Right, it's climbing from 2,000 to 5,000. So the pilot sets this pitch mode, sets the vertical speed. So the pitch mode goes to this vertical speed mode with a speed of 2,000 feet per minute. Okay, so it's climbing at 2,000 feet per minute. Then the pilot also sets the throttle. So this is the airspeed to so much. Okay, it's not so important. Now the plane is climbing. So it's going through 3,500 feet, and the wing flaps are up. So remember, it was trying to land, and then it went back up. So typically, when the plane lands, the slats, which are so if you've seen a side view of a wing, there are these things which extend out, right? Those are the slats. So the slats retracted because it's going back up. Okay. And then the captain then made a physical change. So he changed the pitch mode to IAS. Okay, so what is IAS? IAS is climb while maintaining airspeed. So the pilot had set a certain airspeed, and then he says, okay, now keep climbing while maintaining this airspeed. Okay, so this clamps the airspeed at this value. Okay, so the part of the system dealing with airspeed goes into a fixed mode. Now then what happened was, as the plane was climbing, reaching 5,000 feet, suddenly the system automatically changed the pitch mode. So remember here what happens is the captain physically changes the pitch mode into IAS. What happened here is that the autopilot software internally changed the pitch mode to alt cap. Okay, so what is this alt cap? This is a different mode which is used to end the climb smoothly. Okay, and a side effect of alt cap is it disarms the original altitude capture. So the original altitude capture which the pilot set was climb to 5,000 feet and stay there. Okay, so what happened was internally the autopilot made a setting which disabled what the pilot had set originally. Okay, and then around that time, sort of a race condition, the captain changed the vertical speed to 4,000 feet per minute. Right, so it was climbing at 2,000. He changed it to 4,000. So what happened was this: the plane was climbing, and then it reached 5,000, went close to 5,000, and the captain expected the plane to just keep staying at 5,000, should just level off. What happened instead is the autopilot disabled the altitude capture, and then the pilot increased the speed, so the plane jumped up, right? And the pilot said, "Oops, it didn't arm," right? And the plane was actually almost, it was heading into the airspace for a different aircraft, right? So it was almost the bust situation, but the pilot, took manual control, halted the climb, and then brought it down. Okay, so this is a missed a case. So there was no accident, no incident, but it was a near miss. Okay, so then they went back and said, okay, what was the problem? Why did this happen? And the problem is that the mental model that the pilot had of the state machine inside the box, inside the flight control system, was the pilot's mental model was different from the actual state machine. Okay, and so that's what is a cause of an automation surprise. Okay, so let's actually view this situation using state machines, because we've studied in the class, so we know how to model these systems. So you can actually capture these mental models with state machines. So here, you have a state machine which corresponds to the actual design, and then you basically ask a pilot, right? What do you think what is your conceptualization of how the system works? So the pilot, based on his answers, you can draw out a state machine, right, which corresponds to the pilot's view of what's inside the box. So now you have these two state machines, right? And then, since we've studied all these techniques in the class, we can use the techniques for comparing state machines to figure out if the pilot's mental model state machine, really is a correct view of the system, the actual state machine. Okay. So here's the pilot's mental model for this particular situation. You start in this mode, capture is not active. This is only the relevant part of the mental model. So the pilot can change the pitch mode to IAS or V speed, and it will stay here. At some point, the pilot indicates that altitude capture mode must be enabled. So then it goes to this mode. And when altitude capture is disabled, it goes back here, right? So if capture is enabled, you go to this blue mode. If you toggle it, it goes back to the red mode. Okay, now from capture, there's this other mode that you can reach, but that's irrelevant for this discussion. Now the pilot, the critical thing is the pilot had the following view. So the pilot's view was, once I've put it into the capture mode, as long as I can basically toggle the airspeed and the vertical speed any way I want. So I can basically provide IAS or V speed input, and the system will stay in this mode. Okay, so the pilot's view was changing these control inputs will not do anything to the altitude capture mode. Okay, what was actually happening inside the machine was a little different. So inside the machine, you really had a state chart-like structure. So when the pilot arms the altitude capture, it starts in this initial substate. Okay, but the autopilot was coded such that whenever the plane nears 5,000 feet, the target capture, it automatically goes into this mode from where it disables altitude capture. Okay, and it disables altitude capture anytime either IAS or V speed is changed. So what happened in the previous setting in this was the captain actually changed the pitch mode to IAS, right, and then he changed the V speed. And that's what caused this altitude capture mode to be exited, and it went back into the capture not armed mode. Okay, so now if we compare these two state machines, what we can see is that there is a behavior in the actual system, namely this transition, which doesn't show up in the mental model, right? So here, from this altitude capture mode, if I provide input, either if I change the airspeed or the vertical speed, it goes back to this mode. Whereas here, the pilot's view was, I can do any changes to the airspeed or vertical speed, and I'm going to stay in this blue mode. Okay, so what we'd actually like is that the set of all behaviors or traces or executions of this state machine must be a subset of everything here, right? So everything the pilot thinks the system should do should be a real behavior. Okay, and that's when the pilot won't provide a wrong input, right, which will mismatch with the actual implementation. So what we want is actually language containment, right? We've studied that in the class. What we want is that the language or the trace of this state machine must be a subset of the language of that one. And in this case, we don't have language containment. And in particular, you can also use simulation instead of language containment. So instead of saying language containment, you can say that this state machine must simulate this one. Okay, so every step the actual system can make can be imitated by the mental model. And in this case, you see there's actually a step here, this particular green arrow, which doesn't have any corresponding step in the mental model. And that was the problem. Okay, so So this was the issue. Since then, people have realized this was, I think, the use of finite state machine modeling was, for this purpose, was pointed out about 10 years ago. And since then, I think there's more acceptance of this idea, but I wouldn't say that people are still doing this. Okay. All right. Yeah, Rafael.
But in this particular case, it seems, getting back to the slides, this one, actually, not by the description of this one.
Yeah.
Right, so it seems unintuitive to me that
Yeah.
right, even though it's still in the on-pilot mode,
Yeah.
when it's approaching them, how would it disable the target?
Right.
The target attitude?
It's a good question. I don't know why. So the issue is not who is correct, right? Maybe the pilot is correct in this case, and the system was coded wrongly. But the problem is you want to make sure they're in sync, right? So either system could be wrong, and that's a different problem. But this problem is you just want to make sure that the pilot's view matches what the system actually does. Okay, and of course, then if the designers think this is actually a wrong thing to do by the autopilot, then you should go and change the autopilot code. But then you should make sure that the pilot's mental model is still matches whatever the new code says. Right? Okay. All right. So that's all I have for this lecture today. I think one of the issues here, so what we talked about was, we talked about faults arising in sensors and in computers. We talked about how you can deal with faulty sensors using intervals, deal with faulty computers using redundancy, n-modular redundancy, voting. We talked about synchronized versus unsynchronized implementations. Then we talked about mode confusion, and how to make sure that the mental model of the human operator is in sync with what the system is actually doing. So one of the things that people are really trying to do is they often embedded systems are built up by components that are made by third parties, right? And so if there's one company that deals with everything, it becomes much easier because you have control over what every component does. But if you're integrating components from many different companies and they don't reveal all of the details of how those components work because of proprietary reasons, then it becomes much harder to assure yourself of the correctness and reliability of systems. So we need there's still a wide open area. You need compositional methods for doing for checking if the system does what it's supposed to do and implementing fault tolerance. As compared to 10 years ago, we have certainly a lot more automation. So we have these verification techniques we talked about in the class, which are much more advanced today than they were many years ago. But there's new challenges. So people are putting machine learning systems inside things like flight control systems, right? And so what the system does is actually adaptive, right? It's not in the code. It's based on data and the history and so forth. And so there are interesting issues of how do you verify and analyze the reliability of adaptive systems where the design is not fixed a priori, but it could actually change over the lifetime of the plane, for example. So there's lots and lots of problems in this area to be solved, but I think what we went through today was just a quick tour of some of the issues that you have to think about when you deal with, when you try to build fault-tolerant systems. Okay? Any questions about this? So like I said, this is not on the syllabus, but if you're interested, I can point you to a few relevant papers on this. There's no one source of information for this material, but I can point you to information about some of the case studies you went through today as well as the underlying techniques. All right? Okay, so see you on Thursday.